Hello, chemistry students, Professor Sean McMahon, and this is lecture 4 for chapter 7, chemical reactions and quantities. So in our last lecture, we finished discussing stoichiometry, which is basically a fancy way of saying I can predict or estimate how many grams of a product being produced based on my initial conditions. So the basic rules for stoichiometry, if you remember, were you need a balanced chemical equation. Whatever units they give you, you have to convert that to moles. Then with the balanced equation, we can use the coefficients and do a mole-to-mole ratio to get to the desired compound that they're asking for. And then if the desired compound, if they don't want just moles, if they want grams or something else, we can convert that. But the basic map that we were doing were grams of a given, so this is what they give you, to moles, then using your mole ratio to get the moles of what you want to the grams of what you want. So now what we're going to realize is that these reactions, on paper, they look kind of perfect. So what do I mean by that? If I have 1 slice of cheese, 2 slices of bread, I make 1 cheese sandwich. This is kind of a 1 to 2 to 1 mole ratio. Now, this ratio is kind of, consistent. And what if I don't always have an exact 1 to 2 ratio? So here's an example. I know 1 slice of cheese, 2 slices of bread make 1 cheese sandwich. Okay, so how many cheese sandwiches can I make if I don't have perfect ratios? Well, let's take a look. 1 cheese sandwich, 2 slices of bread, 1 sandwich. 1 slice of cheese, 2 slices of bread, another sandwich. 3 slices of cheese, 2 more slices of bread, another cheese sandwich. So essentially, I still have 2 slices of bread left, but I don't have any cheese. So I can no longer produce any more cheese sandwiches. I'm done. Why? Well, I have excess bread, but I ran out of cheese. If you run out of cheese, you can't make any more bread. So that's basically what happened. I am limited to the number of sandwiches based on one of the reactants. And that's referred to as a limiting reactant, sometimes a limiting reagent. So just like with making sandwiches, reactions can also occur where one of the reactants get consumed up before the other one, and it determines how much product is formed. So limiting reactant problems are pretty much the same thing that we did earlier with stoichiometry. I just call it a double stoich because instead of them just giving you the amount of one reactant, they give you the amount of both reactants and then ask for how much product is produced. So what you do is you do stoichiometry, grams to moles, moles to moles, moles to grams twice, and whichever is a smaller amount is the amount that you actually produce. So here's an example. How many moles can be formed if you begin with 0.552 moles of aluminum and 0.887 moles of chlorine? Now, they could word this a little bit better and say how many moles of your aluminum chloride. But basically, I want to know how many moles of this I can produce. So right away, there's a balance equation, and I want to know a quantity. So I know stoichiometry, okay? But in a limiting reactant problem, they'll give you 2 quantities to start with. So you essentially start with a double stoich. You do each quantity. So I'm going to convert the 0.552 moles of aluminum to moles of aluminum chloride and the 0.887 moles of chlorine to moles of aluminum chloride. So how am I going to do that? Well, I start with 0.552 moles of aluminum. There's 2 moles of aluminum to 2 moles of aluminum chloride. The moles of aluminum cancel. I'm left with units of moles of aluminum chloride, which is 0.552 moles. Then I do the same thing. I run the calculation. That's why it's called a double stoich. right? So this is a double stoich. Why? Because now they're giving me the amounts of both. I start with a 0.887 moles of chlorine. I see in my balance equation, there's 3 moles of chlorine for 2 moles of aluminum chloride. The moles of chlorine cancel. I'm left with moles of aluminum chloride, and I see 2 amounts. So which one do I pick? I picked the smaller amount. Just like with the cheese sandwiches, there was only 3 slices of cheese and 8 slices of bread. So I could only make 3 cheese sandwiches, and I had excess bread. So the limiting reactant, the one that gets used up, is the aluminum. Why? How do I know that? It produced, basically in that analogy, the 3 cheese sandwiches, the smaller amount of product. So this is it's called your theoretical yield. This is in theory on paper. If everything occurs perfectly, this is how much I'm going to produce. This is my yield. And this would be the limiting reactant, aluminum, which gets used first. Does it always have to be mole to mole? No, it might be, like we were doing the other calculations with Stoich, gram all the way to gram. So what is the maximum amount of ammonia in grams? So I want to know how many grams of ammonia from 45.8 grams of nitrogen oxide and 12.4 grams of hydrogen. So they're giving me 45.8 grams of this and 12.4 grams of this. So this is just a double stoich. I'm going to start with separately the 45.8 grams of nitrogen monoxide and the 12.4 grams of hydrogen. I'm going to convert the grams of both of them to moles. How am I going to do that? Periodic table, molar mass. So there's 30 grams of nitrogen monoxide per 1 mole. It cancels that out. For the hydrogen, there's 2.02 grams per mole of hydrogen. Now that I have the moles of each, so I have moles of NO and I have moles of H2, I convert both of them to moles of NH3. So how do I do that? My balance equation mole ratio. There's 2 moles of NO per 2 moles of NH3. So now that cancels. And then if I go down here, I look for 5 moles of hydrogen, there's 2 moles of NH3. So now the moles of hydrogen in this calculation cancel. So I'm left with moles of ammonia. So how do I go to grams? Once I have moles of this, I can convert to grams using molar mass. In 1 mole of ammonia, there's 17.04 grams. So moles of ammonia cancel. And it's the same thing here. What's nice about the double stoich is you see this last portion is the same because you're converting to the same compound, grams of ammonia. I always tell students, write everything out and then grab your calculator and punch the numbers because that'll actually save you a little bit of time. But when I perform the calculation, I see the smaller quantity between 41.8 grams of ammonia that could be produced by the 12.4 grams of H2. I see that the smaller quantity is actually the 26 grams of ammonia that's produced by the 45.8 grams of nitrogen oxide. So my nitrogen monoxide is my limiting reactant. And I produce, theoretically, my theoretical yield is 26.0 grams of ammonia. Why 3 sig figs? Because the answers started with 3 sig figs. So now here we have a reaction. It's powdered aluminum with iron 3 oxide, produces so much heat that it forms, basically, this is used for railroads, and it produces iron and aluminum oxide. So what if I have 113 grams of aluminum and 279 grams of iron 3 oxide? Can I calculate the mass of iron in grams? So I need to know the grams of my iron. So how am I going to do that? I'm going to convert, again, grams of aluminum to moles of aluminum. I'll convert grams of iron 3 oxide to moles of iron 3 oxide. And then I'm going to convert the moles of each reactant to moles of iron using my balanced chemical equation. And then I'll convert to grams using molar mass. So let's start with the 113 grams of aluminum. Grams of aluminum, how can I convert to moles? I grab the periodic table. I look and see there's 26.98 grams of aluminum per 1 mole. That cancels out the grams of aluminum. Then I need to convert moles of aluminum to moles of iron, because after all, I want iron, not aluminum. So there's 2 moles of aluminum for 2 moles of iron. Now moles of aluminum are canceled, and I'm left with what I want, moles of iron. But I don't want moles of iron, I want grams. So in 1 mole of iron, there's 55.85 grams of iron. So now the unit of moles of iron are canceled. I'm left with grams of iron. But I'm not done, because they gave me both reactants. This is a double stoich, so I can't put this as my final answer because I don't know if it's the theoretical yield or not, because I have to do both and see which one's less. So now I go 279 grams of iron 3 oxide. To convert that to moles, right, I need 159.7 grams of iron 3 oxide per mole. The grams of that cancel. Now I can convert the moles of iron 3 oxide to moles of iron using a mole ratio. 1 mole of iron 3 oxide, 2 moles of iron. So the moles of iron 3 oxide cancel. And I see again, this last portion is the same because I'm going from moles of iron to grams using molar mass. And it's a good thing I didn't stop, because what I'm seeing is that the smaller quantity is actually 195 grams of iron. So this is my theoretical yield. Right? And my limiting reactant is the iron 3 oxide. Why? It's this reactant that dictates how much is actually, or the theoretical production, right? So aluminum is in excess. This is my excess reactant. It's the 2 slices of bread left over, okay? In this class, we're not going to calculate the amount of excess. In other courses we do. I'm going to keep it neat, just having you identify the limiting reactant and the theoretical yield. Let's do it again, okay? So now I have 21.6 grams of C3H6. Now, this isn't propane, it could be something else. So I'll just say C3H6, okay? Because it could be cyclopropane, it could be propene. There's a number of things it could be. Well, I'm going to put, I have 21.6 grams of it. And then, oh, it's propylene. It says it right here. My bad. So it's propylene. And then I have 21.6 grams of nitrogen monoxide. So I have 21.6 grams of nitrogen monoxide. I want to figure out how many grams of acrylonitrile I have. So I want to know grams of this. So how do I do that? Well, again, double stoich. I'm going to convert grams of the given to moles. So moles of this. So I can convert grams of this to moles and to moles of this. And once I have moles of each reactant, I can then convert using mole ratios to moles of the product. Once I have moles of the product, I can use molar mass and get to grams. So again, 21.6 grams, 21.6 grams for each reactant. So I convert 21.6 grams of propylene to moles using molar mass, then moles of propylene to moles of my product. It's a 4 to 4 mole ratio. That cancels. And then moles of my product to grams using molar mass. And I get that, but I'm not done because again, it's a double stoich. So now I convert the 21.6 grams of nitrogen monoxide to moles. How? Molar mass. Cancel out the unit of grams. I do a mole ratio, 6 moles of nitrogen monoxide to 4 moles of the product. This cancels moles of the product to grams. Again, we see this is why I set everything up all at once before I even grab a calculator, because these should be consistent. And then we see that that equals 25.5 grams. So again, what's the theoretical yield? The smaller amount. So I would box or circle this as my answer. If you don't box or circle the answer, I don't know which one you're picking for the final answer. So you would still get credit, like this problem's worth 1, 2, 3, 4, 5, 6, 7, 9 points. But if you don't circle it, because you're not identifying this as the final answer, if you don't circle this, I can't give you the full 2 points. I mean, I can basically say, I don't know why this isn't erasing. I can basically give you a point because you came up with the right number, but you're not letting me know that that's your final answer, because that's how many grams. But in real life, okay, we don't always have complete conversion of reactants to products. And sometimes that complete conversion is a difficult technique and it doesn't actually happen. And we can't actually obtain that in lab. So you might have, you know, from your reactants, instead of going straight to your product, you might have incomplete, right, conversion, or you may even have a side product produced. You might even have contamination. These might not even be pure, so they can't give you the full amount. So we actually get less product than we theoretically believe through our stoichiometry calculation. So stoichiometry gives us the theoretical yield because everything works out perfect on paper. This is what in theory we should get, but we don't actually get what should work out perfectly on paper. So stoichiometry gives us theoretical, but what we actually obtain in lab is referred to as the actual yield. So corporations, when they're making a product, they do all the stoichiometric calculations to determine the theoretical yield. They actually sometimes work backwards. They're like, I want this many grams of product, and they work backwards and go, okay, I need this many grams of each reactant. But they actually might not get that yield. So they want to test their efficiency in their technique. That's kind of what your qualitative, analysis portion, or your qual control in a manufacturing company is. And to rate that efficiency, we do what's called a percent yield. Percent yield is just your actual over theoretical times 100. The higher your percent yield is, the better you are producing this product. The higher efficiency you have, the more profits, the less waste and disposal. So calculating percent yield. Suppose the student performs a reaction and obtains 0.875 grams of copper 2 carbonate, but the theoretical yield according to stoichiometry was 0.988. What's the percent yield? Well, it's actual over theoretical times 100. So he actually performs the reaction and obtains. So this is what he did in lab. But in theory, according to Stoich, he should have got this. But his efficiency is fairly high, 88.6. It's not bad. Now let's try it with some of the calculations we did. When 11.5 grams of carbon are allowed to react with 114.5 grams of copper 1 oxide, we actually obtain, so when you say obtain, that's your actual yield. We actually obtain that many grams of copper. So to determine percent yield, we have to take the original masses of each reactant and convert it to grams of copper to figure out the theoretical yield so we can do percent yield. Because we know what we actually got, but we want to see how good we were. So again, grams to moles, moles to moles, moles to grams. So start with the grams of each given. So I got 11.5 grams of carbon, I convert it to moles using molar mass. Convert the moles of carbon to moles of copper. How? 1 mole of carbon, 2 moles of copper, mole ratio. And then the moles of copper to grams using molar mass. Then I do the same for the copper 1 oxide. I start with the given grams of copper 1 oxide, convert it to moles using molar mass. So in 1 mole of copper 1 oxide, there's 143.10 grams. Then I use the mole ratio. 1 mole of copper 1 oxide gives me 2 moles of copper. So 1 mole of copper, 1 oxide, 2 moles of copper to get moles of copper. And then I do 1 mole, 63.55 grams. And what I see, the smaller amount is 101.7 grams of copper. So this is my theoretical yield. Okay, according to Stoich, the smaller quantity, right? The 3 cheeses got used up first. So I only made 3 cheese sandwiches. Well, it's the same thing. This can only produce 101.7 grams, so there's no more left. So even though this can produce more, it has nothing to react with. It's the 2 leftover bread. So now that I know my theoretical yield and I identify the copper 1 oxide as my limiting reactant, I can go and figure out percent yield because this is actually what I produced. So actual over theoretical times 100, I have an 85.9% yield. So can we do this? Of course, right? So here is propane. I want to do a Stoich. The first thing you got to always do is I got to balance it. So I got 3 carbon, I only got 1 here, so I put a 3. I got 8 hydrogen, I have 2, so I put a 4. So 3 times the 2 gives me 6 oxygen here. 4 times the 1 gives me 4. So that's a total of 10. So if I have 10 on the product side, I need 10 on the reactant. It's 5. 5 times 2 is 10. So now if I have 5 grams of propane and 20 grams of oxygen, what is the theoretical yield of water? So I want to know how many grams of H2O am I going to produce? So again, how do I know this is Stoich? They're giving me a reaction, they're giving me starting quantities, and they're asking for a final quantity grams of water. Stoich. So convert the 5 grams of propane to grams of water. How do I do that? The grams of propane convert to moles using molar mass from the periodic table. Cancels those units. I have 1 mole of propane per 4 moles of water. And then in 1 mole of water, there's 18.02 grams. So these units cancel, and I'm left with grams of water. I have 3 sig figs here, so this has 3 sig figs. Then I go to the oxygen. I have 20 grams. Oops, there's a typo right here. That should be O2. My bad, I'm sorry. I have 20 grams of oxygen. There's 32 grams of oxygen per 1 mole. There's, according to the balance equation, 5 moles of oxygen per 4 moles of water. So moles of oxygen cancel. And then in 1 mole of water, there's 18.02 grams. So I'm left with 9.010. I add the trailing 0 because there's 4 sig figs here and I need 4 here, which is a smaller quantity. So my theoretical yield is 8.17 grams, right? If I produce 6.21 grams of water, says it, what is my percent yield? If I actually produce 6.21, what do I do? Okay, percent yield is actual over theoretical. Now that I identified my theoretical and I have my actual over theoretical times 100 gives me a 66.0% yield because 3 sig figs, 3 sig figs. So we had talked a little bit about how under real life situations, we don't always have, the theoretical yield. It doesn't work out perfect because there's side reactions, there's incomplete conversion, right? So there are some parameters for reactions to take place. So now I'm going to talk about reaction conditions and why we're not getting 100% yield. Okay, so there's 3 conditions for a reaction to occur. First, the reactants have to collide so that they come in contact so they can rearrange the atoms. So you need a collision. Second, you need to collide in the right orientation so that bonds can break and you can form new ones. Okay? And you need enough energy to break the bond. So a lot of times what happens is you have the reactants and they hit each other, they collide, they're not in the right orientation, so they just bounce off. Or they collide, they're in the right orientation, but not with enough power, so they don't break the bonds and they just bounce off. So you need all 3. So the energy that's required, the minimum amount of energy to break the bond is called activation energy, but the activation energy also has to take into account orientation and collision. So you could have molecules that are traveling fast enough with enough energy to break a bond, but if it's not in the right orientation, they'll just bounce right off each other. Or if they don't even collide, there won't be a reaction. So I need all 3. So activation is the amount of energy required to break bonds. If the energy of a collision is less, then the molecules will just bounce apart. Many collisions occur, but not all of them lead to product. That's why we don't get complete conversions. So I tend to say, I tend to say the collisions that actually break bonds and make new ones, so that activation energy, I call them effective collisions, because they effectively collide at the right orientation with the right amount of energy to effectively make something. You could have a collision and it's not effective because it just bounces off, it doesn't have enough energy or the right orientation. So many collisions occur, but only few are effective collisions. So typically when we were discussing heat energy, exothermic, endothermic reactions, we were writing, here's the potential energy of, a reaction. So potential energy has to do with each atom has protons, and then there's electrons in the bond. The further the electrons are from the protons, the more potential energy. So my reactants, right, they have a certain potential energy based on the size of the atoms and the molecules and the bond distance. So do the products. If the reactants have more potential energy than the products, then the excess that's released, right? When I lose this energy, remember we said Q equals negative, right? Heat is negative because I'm losing energy, and that's an exothermic reaction. What I didn't talk about is I don't just go straight down, right? I need activation energy for it to occur. And the activation energy is what I was just talking about with the effective collision, right? So like if I put wood in a fireplace to combust, it's an exothermic reaction. Why? The wood has a higher potential energy than the simple compounds of CO2 and water. Okay, so the excess energy is released in the form of heat. It's negative because you're losing the heat to the surrounding. That's why we burn wood. So it releases heat and warms our house. However, if I put a log in the fireplace, it just doesn't start burning. I need the correct amount of activation energy. That's why I need something to catalyze the reaction. I spark it. I turn on the reaction, okay? On the flip side, if my reactants are lower in potential energy and the products are higher, that excess energy that's absorbed means Q is positive. So I have to put energy into the system. It has to enter. It's endothermic. But what I'm not letting you see, or I did, but now what we're saying is there's still an extra, it doesn't go straight here. There's an extra amount of energy to get it there first. And that minimum amount of energy is the activation energy. And it's higher in energy because at one point in time during an effective collision, I have simultaneous bond breaking and bond forming. So I may have cases where I expand an octet and have a really highly energetic intermediate step where it's both reactant and product. That's why it's higher in energy than even the product that has a higher potential energy than the reactant, okay? So what we're talking about when we talk about activation energy is the hump, right? Well, actually from this point, it's all the way up. And from here, it's just this hump right here. But you have to go all the way to the very top of the hump. That's the minimum amount of energy for it to take place. The minimum amount of energy is called activation energy and represents an effective collision. So the amount of heat absorbed or released during a reaction, we talked, is the difference between the energy of the breaking bonds and the reactants and forming bonds in the products. So we used Q equals MCAT, but that's typically when we talk about systems like water, and I'm raising the temperature of water. When we deal with reactions, we use the symbol delta H, and delta H is basically enthalpy. And enthalpy is just heat at constant pressure. So a lot of times you see Q subscript P. Heat, we studied heat energy, Q equals MCAT. When you have a reaction taking place at constant pressure, they just call it enthalpy. And really what this is referred to, this delta H, is the heat of reaction. And the heat of reaction is the difference between the heat of the products and the heat of the reactants. So it's this difference right here, okay? So for your enthalpy of reaction or your heat of reaction, you can use the signs, whether they're negative or positive, to determine whether it's exothermic or endothermic. So for an exothermic reaction, just like Q can be negative, lose heat, Q is for a system. For a reaction, if it's negative, it's exothermic because the reaction is releasing energy, heat. Combustion's a perfect example. I burn wood. Why? Releasing heat and energy. It's losing heat, heat is leaving, it's exiting, it's negative. For an endothermic reaction, heat must be absorbed to drive up to a higher potential energy for the product. So heat is absorbed or it enters, that's an endothermic reaction, and the enthalpy of reaction or the heat of reaction is positive. So for exothermic, how would they indicate it? There's two ways. They can show you in the reaction if it's exothermic. So here's a case of an exothermic, there's excess energy. They would just write the heat value on the product side because they're saying it's producing heat. It's releasing the heat. So if it's exothermic, they could write the heat on the product side, or they don't even include it in the balanced equation. They just write delta H equals, and there's a negative to show you that it is exothermic. In an endothermic reaction where heat must be absorbed, now they could do two things. They can write the heat on the reactant side because we need energy to go to the higher potential energy of this product. Or if they don't include the heat in the reaction, they'll just write the enthalpy of reaction or the heat of reaction to the side of the reaction and they'll put a positive. Or they won't make it negative. It'll be positive because heat is entering, it's absorbing. So that's what enthalpy is, the amount of heat emitted or absorbed, and it depends on the reactants and whether or not they're actually going to react. So in this example, they don't include the heat in the balanced chemical equation, okay? And this is propane, the combustion. But on the side, they're saying the heat of reaction is negative. So this shows me this is an exothermic reaction. It's releasing 2,044 kilojoules. But when does it release the 2,044 kilojoules? When 1 mole of propane burns in the presence of 5 moles of oxygen to produce 3 moles of CO2 and 4 moles of H2O. So that's a mole ratio, right? So I can literally write, well, if 1 mole of propane is burned, it's going to release 2,044 kilojoules of propane. And I can actually make it a mole ratio. Or if 5 moles of oxygen burn in the presence of propane, then 2,044 kilojoules of heat will be released. How do I know it's released? It's negative, it's exothermic, and I can make a mole ratio. So why is that important? Well, I can do Stoich. I can convert the 13.2 kilograms of propane to grams of propane to moles of propane. And when I know moles of propane, guess what? 1 mole of propane gives me this many kilojoules. I can convert it to kilojoules of heat. So how would I do it? All right, well, 13.2 kilograms. How can I convert kilograms of propane to grams? In 1 kilogram, there's 1,000 grams. Okay. Now what do I need to do? I need to convert grams of propane into moles of propane. And then 1 mole of propane, if that burns, according to my balanced equation, then I'm going to release 2,044 kilojoules. The negative sign makes a difference because it's telling the direction, whether it's being released or absorbed. So I have to calculate molar mass of propane. So 3 times 12, 36 plus 8, roughly 44.03, 11 grams of propane. Oh. So that's basically the calculation I just did, right? Now, you know, I made it 1,000 grams per 1 kilogram. Well, remember, 1,000 is just 10 times 10 times 10, which is 10 cubed. But everything else, it's exactly right. I see my units canceling. I get my final answer. So let's try another one. Because this is all still stoichiometry. The difference is now, instead of me determining how many grams of a product I produced, now I'm interested in how much energy I release. It's still using a balanced chemical equation to determine an amount of something. Instead of grams, now I want heat. It's still a quantity. So the landing module for the Apollo mission used a fuel made of hydrazine, N2H4, combined with an oxidizer, dinitrogen tetraoxide. How much heat is produced from the reaction of 273.9 grams of N2H4? So what do I have to do? I have to convert grams of N2HO4 into moles of N2H4. And then when I have moles of N2H4, I can convert it to kilojoules. How come? 2 moles of N2H4 will give me or release 1,049 kilojoules. So I start with grams of N2HO4. How do I convert it to moles? Molar mass, rules of stoichiometry. Whatever they give you, convert to moles. If they give you 2 things, convert both to moles. It's just double stoich. So now they're giving me 1, so I'm converting it to moles, okay? So I have grams of N2H4, 1 mole. Now, I don't have to convert to moles and then to grams because they're not asking for grams of a product. They're asking for heat. So I could just say, oh, well, there's 2 moles of N2H4 per 1,049 kilojoules released. When I do the calculation, I get this. And what I see is this is an exothermic reaction. It's releasing energy. So last but not least, military meals ready to eat can be heated on flameless heaters using the reaction below. So magnesium plus H2O yields magnesium hydroxide and hydrogen gas. The reaction is exothermic. How do I know? It's negative instead of positive, and releases 353 kilojoules. How many kilojoules of heat are produced if I start with 25 grams of water? So I'm going to convert grams of water to moles of water. And then I convert moles of water to kilojoules because there's 2 moles that release negative 353 kilojoules. So I start with 25 grams of water. There's 18.02 grams of water per mole. Grams cancel. And 2 moles, where did I get 2 moles of water? My balanced chemical equation, there's a negative 353 kilojoules of heat released. So my final answer has 3 sig figs, because that's a trailing 0. And I keep the negative to show that it's exothermic and that the heat released or is produced. So that is chapter 7, reactions and their quantities. So again, in lecture 1, we balanced chemical equations and identified the first 3 of the 5 basic equations, which were combustion, which we're seeing a lot, combination, decomp. In the second lecture, we went over the 2 more difficult reactions because they're aqueous, and we had to take into account solubility rules, were double displacement and single displacement. In the third, we introduced the concept of counting by weighing using moles and using molar mass for elements and molecules. And then we converted moles to mole ratios in balanced chemical equations, and then expanded our stoichiometry for not just mole to mole calculations, but grams all the way to grams. And then in this lecture, we continued our stoichiometry calculations, but brought up the issue that in real life, you don't have complete conversion. So you sometimes have to use theoretical yield to you use theoretical yield, stoichiometry to determine a theoretical yield, and you use your actual yield in lab to calculate percent yield. And sometimes you also have 2 reactants where one gets used up first. So you do a double stoich to determine which one's the limiting reactant and which one's the theoretical yield. And then lastly, we used stoichiometry and mole ratios to do heat calculations for balanced chemical equations as well. So thank you for your patience. I appreciate it. This chapter is critical as we move forward to gas laws and solution chemistry, because we will continue our stoichiometric calculations and our double stoichiometric calculations with limiting reactants. So thanks for watching, and I'll see you next time.